Hello, Physics 20s. In today's lesson, I'm going to talk to you about what a gravitational field is and identify what is the source of a gravitational field and what things can a gravitational field influence. Learning outcomes are to 1. Define the term field as a concept that replaces action at a distance and apply the concept to describe gravitational effects. And then 2, relate qualitatively and quantitatively using Newton's law of universal gravitation, the gravitational constant, to the local value of the acceleration due to gravity. For outcome 1, I'm going to define field a little bit differently. All right, so what exactly is a gravitational field? A gravitational field is a region of potential influence surrounding a mass, and I'm going to call the mass that produces the gravitational field M1. It turns out that any object, as long as it has mass, well, I mean, that's what an object is. An object has mass, produces a gravitational field. However, most masses are too small for this to have any noticeable effect at all. So usually when we talk about gravitational fields, we're mainly interested in the gravitational fields produced by planetary bodies. Okay, so I have a large planetary body, M1. In the regions surrounding this planet, there is a gravitational field. In fact, there's a gravitational field within the surface as well. The reason I called it a region of potential influence is because even though there is the field there, it doesn't necessarily have to do anything. So in this current picture, there are no objects that are anywhere near the actual big planet M1. If there are no objects near the big planet M1, then that planet doesn't do anything. However, if you take a smaller mass and you put it into the field, then it can have an influence. And that's what gravitational fields do. They can influence smaller masses. An example of this would be, so a planet being the source of a gravitational field, and an object in the field might be a satellite. So a smaller object like a satellite is influenced by the gravitational field produced by the planet. To determine the direction of a gravitational field, it is determined by 1, taking a small mass, which I'm going to call M2, and placing it in the gravitational field. This small mass, M2, could be an astronaut, it could be a space station, it could be a moon, it could be a satellite, but its mass is quite a bit smaller than the mass of the planetary object. What we want to know is, to figure out the direction of the gravitational field, we just simply put the small mass into the field and then identify what direction would the force of gravity be acting on that small mass. Well, think about this. If you drew a free body diagram of M2, there would be one force acting on it. It'd be a gravitational force, and it would be pointing towards the center of M1. So the direction of the gravitational field is just the direction that a small mass would go if you put it into the field. So in this situation, the field actually does have an influence. But once again, if you remove the mass, then even though there is a field, it doesn't do anything. And hence why I'm describing it as a region of potential influence. You need to have a mass there for it to actually do anything. To deal with the direction, we like to represent the direction of a vector field with field lines. And here's how we draw gravitational field lines around a planetary body M1. We've already identified this. The direction of a gravitational field is the direction that a small mass would move when placed in the field. A small mass in the field if it wasn't already in motion. So if you just put the mass there at rest, what direction would it go? It doesn't matter where you put a mass. For example, if you put a small mass up here, we put M2 up here, the gravitational force would want to pull towards the center of M1. So the direction of your gravitational field, which we use the vector g at the vector sign, would just be directed straight down. If we put a small mass, m2, over here, again, it wants to go towards the center of the planetary body. So this vector would be directed down and towards the left. We can actually summarize that direction a bit more concisely just by stating that the direction of a gravitational field surrounding a planetary body is directed radially inward. I mean, you could think of like there being a large circle that just surrounds, like kind of like connects these different lines together. And you could think of the radius of the circle as being from like the center of M1 to like the outside. And then the direction of the radius would always be directed inward, hence radially inward. Field lines can also communicate something about the magnitude of the field to us. So when we draw gravitational field lines, and I would say for drawing gravitational field lines around like a large planetary body, like at least 8 of these field lines is necessary. Just because there's not a field line, for example, at this point where I have x, doesn't mean the field is 0. It has everything to do with like how much space there is between the field lines. So for example, if we get close to the actual center of the planet and I try to figure out the distance between these different vectors. So for example, I might have one vector that goes across like that. Let's pick a different color so we can see it a bit better. A distance from here to this vector, that's called an arc length. And if we compared it from here to there, well, this bottom distance, these lines are much closer at the bottom compared to at the top, which tells you the gravitational field, the region of influence, is stronger as you get closer to the center of the planet. And it's much weaker because these lines are more spaced out the further away you are. I think that's pretty intuitive. You expect the gravitational field of a planetary body to have more influence the closer you get to it. What we want to do is calculate the magnitude of this gravitational field, so identify how strong it is. The magnitude of the gravitational field is what we refer to as the gravitational field strength. I like to ask my physics 20s in advance what factors they think contribute to making the field stronger, and usually I get the following 3 responses. Usually the one response I'll get is if M1, the source mass, is bigger, then there's a bigger region of influence. For example, if this was the Earth and you replace it with Jupiter, which has a much larger mass than the Earth, then it has a larger region of influence. And that is correct. The bigger the source of the field in terms of its mass, the bigger the gravitational field strength. The other one is dealing with distance. So as you get closer and closer and closer towards the large planetary mass, then the region of influence is larger. The other one, though, and this one is the one that's not correct, is sometimes students will say, well, if M2 is bigger, then the gravitational field strength is going to be larger. Now, here's where we have to be careful in distinguishing between the force of gravity and the gravitational field strength. They're not the same thing. If M2 became bigger in mass, yes, I completely agree, the force of gravity between them would be larger, but that does not mean the gravitational field strength at this location is bigger. And I'll actually prove that mathematically in a moment, why the mass of M2 does not matter. So the magnitude of the gravitational field, which we could represent with the variable g at the vector, absolute value, which is the same thing as the acceleration due to gravity. So we can use the words gravitational field strength, magnitude of acceleration due to gravity, and magnitude of the gravitational field all interchangeably. 2 equations to calculate this. One, this equation's on your formula sheet, and it tells me that the gravitational field strength is equal to g, the gravitational constant, times m1 divided by r squared. Or we can use this equation. The gravitational field strength is equal to the magnitude of Fg divided by m2. In these equations, m1 is the source mass. So it's the thing that's producing the gravitational field, which is likely a planetary object. I should point out, though, on the formula sheet, they don't add the little subscript here. They just write down gm over r squared. So it's up to you to understand that it's m, the source of the field, that's actually resulting in there being a gravitational field. m2 is the mass of a smaller object that's in the field. And then once again, on the formula sheet for equation 6, we don't see the 2 attached here. So we need to understand that this is dependent on, or this mass here is referring to the smaller mass that's in the region of the gravitational field. R, and you gotta be careful about this because planets have size, R represents the distance from the center of the planet to the location that you are interested in. So let's say that I was interested in the gravitational field at the location of this satellite or this mass M2. So R would be the distance from M1, the center of M1, to whatever point I'm interested in. Now, the equation 5, so that's the one that's G equals gm1 over r squared. We can derive that using Newton's universal law of gravitation. So as a quick recall, universal gravitation equation is Fg is capital G m1 m2 over r squared. We also have another equation to calculate Fg. That's the one we use for most of the dynamics unit, which tells us that Fg is just equal to the mass of an object times the acceleration due to gravity magnitude. Let's put the two of them together. Fg is equal to Fg. So then I would have gm1 m2 over r squared is equal to m2 times g. Well, how would this equation simplify? What variable could I get rid of? If you divide both sides of the equation by m2, they cancel off. So going back to that previous point, like why does the mass of an object in orbit not matter in terms of the gravitational field? Well, I just proved it mathematically. I showed that the m2 values do cancel off. And then you get a g value, which is equal to gm1 over r squared. And just to further illustrate this point, so let's say we add here's the surface of the Earth, and here's one mass, m2, and here's a much bigger mass, m2. They both accelerate at the same rate. They both accelerate down at 9.81 meters per second squared. The force of gravity acting on them is different, but the actual rate of acceleration is the same. So you may have heard something along the lines, if you have a few objects, one is heavier than another one, which one hits the ground first? Well, if they have the same shape, they should all hit the ground at the same time. Of course, if you actually factor different shapes into account, then you have to deal with air resistance, in which case the acceleration would not be the same. But if we're assuming the objects are free falling, then the mass m2 does not matter. Now, on the surface of the Earth, we can actually get our value for the acceleration due to gravity or the gravitational field strength. We'll just plug numbers into that equation. So on the surface of the Earth, the gravitational constant is 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared, multiplied by the mass of the Earth, 5.97 times 10 to the 24 kilograms, divide by the Earth's radius, 6.37 times 10 to the 6 meters, all squared. And I want to point out again that all three of those numbers, the gravitational constant, mass of the Earth, and radius of the Earth, are all on the formula sheet. Let's see what units cancel here. So the meters squared in the gravitational constant would cancel off with the meter squared in the denominator. And one of the kilogram units would cancel off. That would lead you to an alternate unit you can express gravitational field in. We're used to writing acceleration due to gravity in terms of meters per second squared. And that was useful from a kinematics approach. From a kinematics approach, it was telling us for every second how much was our velocity changing. But now we're kind of like looking at from more of a dynamics approach. So it turns out the units, newtons per kilogram, is equivalent to meters per second squared. I'm not going to show that, as that's going to be a problem in the assignment you need to work on, but they are equivalent. So what does this mean? Or how do you interpret this? Think about it like this. If you have a gravitational field of 9.81 newtons per kilogram, it would mean if you had a 1 kilogram object at this location, it would experience a force of 9.81 newtons. If suddenly this gravitational field changed to, for example, 19.62 newtons, the way I would interpret that is if you had a 1 kilogram object at that location, then it would be subjected to a force of 19.62 newtons. So it's a different way of thinking about it. For meters per second squared, we're thinking about how much the velocity changes in 1 second. In terms of gravitational field strength, we're looking at, okay, per kilogram of mass, how much force would that kilogram of mass be subjected to as a result of that gravitational field? Okay, so just one example. I have a person that is 1.914 times 10 to the 7 meters above the surface of the Earth. Well, let's sketch that. So let's say this is the center of the Earth. And here's the Earth's surface. And our object is way above, so somewhere up here. And we'll say this we call this the altitude. So the distance above the surface of the Earth, our altitude, would be equal to 1.914 times 10 to the 7 meters. We've got to be careful with this, because whenever we talk about calculating, let's label these masses here. So we'll call the center of the Earth M1, and we'll call this M2. R is a distance from M1 to M2. So we need to factor in the Earth's radius. So this would be R for the Earth, and then the R value we're going to look at would be from the center all the way, center of mass 1 to the center of mass 2. That's the R value. So R is going to be equal to the altitude plus the radius of the Earth. Okay, so what do I want to do? I want to calculate the gravitational field strength at that point. I should just point out, by the way, you don't need the mass to even be there. Like, whether the mass is there or not, like, there is a gravitational field and we can calculate it. We don't need mass 2 to do this calculation. Not for part A anyways. Okay, so how do we calculate it? My equation, the magnitude of my gravitational field strength is equal to G M1 over R squared. Plug numbers in. The gravitational constant is 6.67 times 10 to the minus 11 newtons times meters squared per kilogram squared, multiplied by the mass of the Earth, 5.97 times 10 to the 24 kilograms. Divide this all by R squared. Okay, now here's where you have to add both the altitude and the Earth's radius together. So R would be 6.37 times 10 to the 6 meters plus 1.914 times 10 to the 7 meters. And we square this, and then we get G would be equal to, I get a value to 3 significant digits of 0.612 newtons per kilogram. This result shouldn't be surprising, by the way. On the surface of the Earth, G is 9.81 newtons per kilogram. Because of the inverse square relationship between G and R, it tells you that as R gets bigger, G gets quite a bit smaller, and it does decrease quite a bit. It's down to 0.612 newtons per kilogram. And the way to interpret that is, at this location, if you had a 1 kilogram mass there, it'd be subjected to a very small force of 0.612 newtons. B. I want to calculate the force of attraction between the person, M2, and the Earth. And it gives me some extra information where it tells me what the weight of the person is on the surface of the Earth. It turns out there's actually two ways you could do this calculation. We could calculate the force of attraction between the person and the Earth using universal gravitation. We could use Fg as G, M1, M2 over R squared. Or we could use Fg is equal to the mass of the object times G. Either of those will work. However, I can't do that calculation right now because I'm missing a specific piece of information. The piece of information I don't know is I don't know the object's mass. So we can actually calculate that though, because it tells me what their weight is on the surface of the Earth. So if I know their weight on the surface of the Earth, I can figure out their mass. Okay, so let's look at the Earth's surface. Okay, so on the Earth's surface, we have we can use the equation Fg for their weight is equal to m2 times g. So their mass, m2, would be equal to their weight divided by g. This is on the surface of the Earth. We know on the surface of the Earth their mass is 400 newtons, and g is 9.81, and I'll write down newtons per kilogram. Doesn't matter what unit you write, by the way. Newtons per kilogram, meters per second squared, they're both the same thing. Okay, this would give me a mass to 4 significant digits. I'll keep one more than I need in intermediate calculations of 40.77 kilograms. Now that I have M2, I can use either universal gravitation or a simple weight equation to do this. Well, I'm going to use the weight equation because it's easier. So I'll say at your altitude, just reuse the same equation. So I'd have Fg would then be equal to m2 times g. M2 is the mass of this astronaut, so 40.77 kilograms. Multiply by, well, at the altitude, our gravitational field strength is much weaker, so it's 0.612 newtons per kilogram. And not surprisingly, their weight is quite a bit smaller if you have a larger altitude, and I get to 3 significant digits, a weight of 25.0 newtons. All right, so that's it for this lesson, and you can practice work on the assignment called Gravitational Fields, and then I believe next time we'll get into a discussion more so dealing with satellite motion, and I'll talk to you then.